Now we have the leader at the accept phase. And during the accept phase, it might get contacted by a promise from a replica. And we are going to handle this case now. So let's understand the situation. The acceptor was in the prepare phase. It got a promise from a majority of replicas, and it sent accept sync to synchronize its state with the state of the replicas that have sent a promise. But what can happen is that we can get a late promise. It's a promise from a replica that arrived after the leader moved to the accept phase after getting a majority, and now we have to handle this accept sync. This accept sync is a little bit different, and we'll see how it is different. Once we do that, then the rest we have is just incremental accepts, and we will see that here, and decisions. So let us take this step by step. So we are talking now about replicas from which the leader received a promise in the accept state. So let us see how we solve this problem. And we are talking now about a leader in the accept state, and he has to perform a synchronizing accept. So as we say always, the leader receives a promise from replica Q while it is in accept state. And as we know, whenever a replica sends a promise, it also sends the length of its decided sequence. We said that. And we knew that in the prepare phase, the leader can reconstruct his own sequence and extend his own sequence. Now for the other replicas, which are the replicas after the leader moved to the accept phase, it is going also to send an accept sync, a synchronizing accept, which is, what is it? It is the suffix at the accepted sequence at the leader at this point, and also from where to append this suffix, which is really just extending its decided sequence at the replica. It has also to do one more thing, and this is important. And with what is that? If some sequence is already decided, so it also send the decide index LD at L. And remember what we mean by that. At any of these processes, we have the accepted sequence, and an initial segment of this accepted sequence is what we call the decided sequence, so the L. So in this case, if before getting the promise message from a replica, some decision has been made by this leader, then this information has to be conveyed to the replica. So let us look to this again. So here is a situation of what we call the other replicas, the replicas that came to communicate with the leader when he is in the accept phase. First, the leader has to wait until it receives the promise from that late replica before sending the synchronizing accept. And this is important because receiving a promise actually leads to synchronizing the leader's knowledge about Q. So they synchronize. The leader's knowledge is now about what Q has, and we also, by this, we are maintaining the invariant that at Q, the decided sequence is a prefix of the accepted sequence. How to maintain this invariant? We do it by making sure that L does not send a decide message or subsequent accepts to Q until the synchronizing accept message has been sent to Q. And because of the FIFO order, we have to send the synchronizing accept first, and later we can send other accept messages and the decision. Now, if some sequence has been chosen before L receives a promise from Q, then L must send a decide message to Q after its first synchronizing accept. And this information, if we remember, is indicated by the variable LC. LC is the length of the chosen sequence so far. When a process or a replica becomes a leader, this is initialized to 0, and once some sequence is chosen and sent to be decided, then this sequence is greater than 0. So that makes things quite easy. So here is the code. We get a promise from a replica A or an acceptor A, and we are talking to the current leader, but he is in the state accept state. So we store this information, remembering that now we have got a promise from that replica. And then we send a synchronizing accept with the suffix of the accepted sequence at the leader, and this is the decided sequence index at the replica. And in case the variable LC is not 0, in fact it means it is greater than 0 because it cannot be negative, then we send also to the replica the new index of the decided sequence. So in this case, this index is definitely larger than this. So this is new information to the replica saying now we have decided on more commands in the log or in the accepted sequence. So let us see how the replica behave. The replica is still a follower and in the prepare state. And this means that we are talking to the current leader. We update NA to NL. This is the round of the accepted sequence. We update our accepted sequence by getting our prefix and adding to it the suffix that we got here. And then we send an acknowledgement to the reader. This is L again. We send an acknowledgement to the reader saying that we have now accepted so far. If this is our VA, so we give really the length of this VA. And we move to the accept state. Once we are the accept state at a follower and accept state at a current leader, we will just incrementally add new commands. And that is what we are going to talk about now. So now we are in a state where any follower has been synchronizing his state with the reader state. So what happened after that? Whenever a reader gets a command, we just send this command to all the acceptors that have already received the accept sync message. So this is what we call subsequent accept messages. We have to think about that everything should be correct. So the basic idea, if we send a message accept with a sequence V1, and then after that we send another accept with a sequence V2, and M1 is sent before M2, and because of the FIFO order, and we are talking about the same leader in the same round, then M1 should be also received at the replica before M2. So L knows the following, that at the time when Q is going to process M2, Q will have accepted V1. Or, of course he doesn't know, maybe Q has blocked round N because a higher leader came, but this leader is still unaware of that. So this holds, of course, because of the FIFO links. Therefore, when a leader will send actually the difference between V2 and V1. So if this part is V1 and this is as a whole is V2, then he is going to send this part only. So that is what we say, it is a suffix of V2 starting after the index that corresponds to the length of V1. And of course it has to send that offset, okay, clearly. As we can see, in our case, we never actually get a command, a propose, and the reader is in the accept phase, we send it immediately. And that's what we're saying here. So if V2 is V1 followed by a new command, then what we do send is actually just send an accept from the leader with that new command. And that will be appended to the sequence after this position, okay? fine. We are now, can show you the implementation. So the leader in the accept phase gets a new command. This is the propose thing. It's the propose. And his state is a leader and accept phase. Then he appends or augments, extends his accepted sequence. And then we are using this map, which is the longest accepted sequence at each process. This is so the longest accepted sequence now at self, at the leader, will be increased by 1. And then for each process, except myself, that have already passed the synchronizing accept. We know that from here. This is really becomes non-zero when you send a promise. Then we send to these guys, to these processes, we send them the accept message with, of course, our round number. A replica that moves to that accept phase will accept the command from the leader if the leader is the current leader with the current round. This is what we call the promise. And it will just extend its sequence and acknowledges the leader. So whenever you get a command and from a process L, and I am as a follower or as a replica in the accept phase, and this says that this process is a current leader, I extend my accepted sequence and I send the index of the new accepted sequence to the leader. And that then we're going to accumulate majority of these to be able to say that we have a longer sequence that is chosen and should be decided. So, and that leads us to how we decide. So that is easy, in fact. Every process maintains what is called the longest accepted sequence. And initially, this is for all processes. It is for n, so it's an array or a map. One position for each process. And it is initially 0. That's what I mean by this. So this is initialized, an array initialized to 0 initially. And this contains the leader's knowledge of the longest accepted sequence per replica, including himself, of course. And LC, as we know, it is the longest learned sequence or the long decided sequence so far. And then when we get an accepted message, remember this is the M is now the length of the accepted sequence. So if the length that came now to the leader of the acknowledged sequence is greater than the longest chosen sequence, means that a majority of replicas have responded. So we have now a longer sequence that is chosen, and therefore we can send a decision to all replicas in this accept phase. We can see it here. So whenever the leader gets an accepted message, M is very interesting now. He is the leader and he's in the accept state. He takes this M and add it in the position that belongs to the replica A. If M is larger than the longest chosen sequence so far, and what is this is saying? This is saying that there are a majority in this array or map that have these lengths or longer. Then we can update the longest accepted sequence. This is actually the definition of a chosen sequence. Then we update LC. We basically extend it. So the longest chosen sequence now is longer. And for all processes that passed the prepare phase, or followers and also leader that pass, everybody, for all processes that pass the prepare phase, we just send a decide. This is basically, and what is this decide is saying? Now you have decided on some length here earlier. Now we are giving you new information. You can decide on a longer prefix of the accepted sequence. So let us now see what happened at the decide. So this was the old decide when we were talking about sending sequences here and there. We had LD, which initially 0, say the length of the decided sequence. And when we get a sequence, we see If its length is longer than LD and we are in the current round, we basically update LD and we decide in that longer sequence. Now, that's not what we are going to do. We are not sending sequences, but we are going to deliver one command at a time. So currently, as we said here, before this, every decided sequence is handed to the application in its entirety. But it makes more sense, of course, to change the API so that we decide on one command at a time. So we incrementally say, now I'm decided on command 5, then I decided command 6. And this is actually quite good because the decision can be taken by a state machine and executing the corresponding command. So here is our initial index of how much is decided. It is 0, and this code is 0-based indexing. If we get a decision saying up to L now is decided, and we get that decision from the current leader, then we basically, while our local L is less than L, we trigger a decision, and then we iterate again until we decide on all the commands in the sequence until LD becomes equal to L. At this point, I want to tell you that we have actually completed our leader-based sequence Paxos. It is quite efficient algorithm, and I'm going to show you in the next unit the whole algorithm again and discuss some issues around it. This algorithm, as it is now, it works in the asynchronous system model, but it requires a perfect FIFO lane abstraction. So, see you in the next unit.